So we're going to, in the problem session today, Anisha is going to go through a couple of the problems, but then there's problem, whatever number it is, maybe 9 on problem set 2. We're going to have people work on together for a bit. Yeah. Because it's a very important problem and fun, in as much as any of this is fun. So we've been working through some of the matrix calculations where knowing the Hamiltonian and the rotating frame is time independent, we have these rotation operators or propagators that take the density operator from one time to another time in the pulse sequence. So, and a really important part going forward is the notion that we can expand the density operator into a set of basis operators. So you already knew before coming here that given an arbitrary vector, you could expand it in terms of unit vectors, for example, along the Cartesian axes. And then when we started, we said, given a set of basis wave functions like alpha and beta, we could write an arbitrary wave function as a linear combination of wave functions. And that in quantum mechanics would then be called the Hilbert space. And now we're going to expand the operators in terms of basis operators, which is then called Liouville space. Now, when you expanded a vector into unit vectors, you had an orthogonality relationship. The unit vectors were such that the unit vector along x was normalized to unit magnitude. So if you took its dot product, you got 1. And it was orthogonal to a unit vector along y. So if you took I dot j, you would get 0. And then when we took the wave functions as the basis, we said that alpha was orthogonal to beta. And this was because we represented them as row vectors and column vectors. And if we did the usual vector multiplication, then alpha was normalized to 1 and beta was normalized to 1, and alpha times beta was 0. So we had a recipe for making the wave functions orthogonal. Now, if we're going to see if we can expand the operators in terms of other operators, we also are going to have some notion of what we mean by two operators being orthogonal to each other and what it means to normalize them to some length, maybe unit length or magnitude or not, but some normalization procedure. So here, for example, we've looked so far at this basis that I had written down before, where this 2 by 2 matrix was IX, this was IY, this was IZ, and this was the identity. And if we multiply these, then what's our orthogonality going to be? We should leave that, we'll leave that for the time. So an alternative basis is shown on the top. I don't know why it's upside down, but so I should say it, where we have I alpha, I beta, I plus, and I minus. And I plus we get from IX and IY by remembering that the definition of I plus is IX plus I times IY, where I is the square root of -1, and I minus is IX minus the square root of -1 times IY. And if we do that arithmetic, we get these two matrices. And then IZ here, remember, represents the difference between the alpha state, the population of the alpha state and population of the beta state. So that this represents population of the alpha state. This represents population of the beta state. If I subtract them and then introduce a factor of 1/2 for normalization, I get IZ, the difference between I alpha and I beta. And if I add these two together, I get the identity matrix. And again, I have this factor of 1/2 for normalization purposes. And this tells me what I already knew is the populations of the alpha and the beta states have to add up to unity because I can't create or destroy. So suppose I have some arbitrary density operator. So it's 4 components. It's for a single spin, it's a 2x2 matrix. And it has 4 components indicated here. But I could write this as a linear combination of sigma 1 times I alpha, that just gives me a sigma 1 here, plus sigma 1 times I plus, that gives me sigma 1 in this position, sigma 2 times I minus, that gives me a sigma 2 here, and then sigma 2 times I beta, giving me this position. So that's rather trivial. Each of these basis operators just gives me back one element in the overall matrix. Or, with a little algebra, I could convince myself that this same matrix could be written using a different set of operators, where I end up with sigma 1 plus sigma 2 times Ix, and then plus I sigma 1 minus sigma 2 Iy, so on and so forth. And you can convince yourself with a little algebra that this is equally good representation of this matrix. So I have 2 different sets of what I would call basis operators here. I haven't shown you that they're orthogonal and normalized yet. That'll come shortly, but it's to make the point that given some basis operators, I can write the density operator in terms of those basis operators. And if I switch basis operators, it's just that the coefficients that go along with the operators change. The coefficients are just numbers. So here is this idea for the Liouville-von Neumann equation. So I'm going to write sigma as some sum over a set of basis operators. Yep.
I have 2 questions about the previous slide.
Okay.
So just to clarify, in this equation, right, we are just writing the same one as this one, but in terms of like expanding I of I plus I minus in terms of Ix and Iy.
That's right.
And so what's the interpretation for the off-diagonal element 1 and 1 in those I plus and I minus?
So we'll interpret those, and there's probably some pictures coming. That I plus represents a coherence between the state beta and the state alpha, because in quantum mechanics, I plus takes the magnetic quantum number from -1/2 to +1/2. And +1/2 we associate with the alpha state, -1/2 with the beta state. And we'll associate that operator with the fact we created some coherence between those two levels in the phase sense of going from beta to alpha. And I minus would be a coherence in the opposite sense, going from alpha to beta, because then we've gone from plus a half to minus half. And coherence, remember, we mean that when we apply the pulse was phase coherent over the sample. If we apply, for example, a Y 90-degree pulse, and we end up with IX magnetization, if we rearrange these terms, IX magnetization is equal to 1/2 of I plus I minus. So that would say a coherence that we think of as IX can also be thought as an equal mixture of I plus and I minus, so that we have coherence going up from or down from beta to alpha and up from alpha to beta. We've generated two kinds of coherences in the new basis. So everything depends on what basis we're talking about. In a Cartesian basis, we've just created IX. But if we want to think of it in this, what sometimes is called the shift basis, where we have the pluses and minuses, then the pulse creates an equal mixture of I plus and I minus. If we instead had applied an X pulse and we generate IY or minus IY, and in terms of the raising, lowering, IY is 1/2I plus minus I minus. So now we have, again, we've generated an equal admixture of the plus and minus coherences, but they have a different phase relationship to each other. Remember, I for us is the same as a pi/2 phase shift, and a minus sign would be the same as a 180-degree phase shift. So we've generated an equal magnitude of I plus and I minus, but they have a different phase, relative phase, than they did when we did the X pulse. Is that okay? So here I'm going to write things more generally. Here's the Liouville von Neumann equation. And now I've said sigma I can express as some linear combination over a set of basis operators. And each basis operator has some time-dependent coefficient. The basis operators are obviously independent of time. So any time dependence has to come from the coefficient. And this turns out to be very useful, which is why we do this. And then on the other side, I've done the same thing. I kind of jumped a step, perhaps, that there should have been the sigma inside the commutator, but these numbers all commute with the commutator because they're just numbers. So I can take the sum outside. And then similarly over here, the time derivative only acts on the coefficients. So I can write that more explicitly, that the time derivative acts on the coefficient. Now, you might recall that we could use the orthogonality relationship of the operators then to isolate coefficients by pre-multiplying by a bra and then forming the integral and make use of orthogonality. So we're going to do the same thing here. So I've pre-multiplied by a basis operator J on both sides, and I've introduced these symbols. So what do I mean by this? This is my recipe for the orthogonality condition for the operator. And what I mean by this is the vertical bar means take the adjoint of the operator on the right. Doesn't really matter, but I always do that. Not the right, the left. The vertical bar means take the adjoint of this operator, and the angle brackets mean then get the trace. And the trace is the sum of the diagonal. So it's a two-step procedure. First, I'll replace b sub j with its adjoint, and then multiply the adjoint b sub j times b sub k, and then take that resulting matrix after I multiply them together and calculate the trace. We set the operator, I don't know which came first, whether the operators were defined and then this operation was invented, or the operation was invented and then the operators were developed to obey it. It doesn't really matter to us. This happened way back when. Actually, I think it's true. Maybe Ann knows whether it's true, but supposedly Heisenberg was working all this matrix algebra out with just columns of numbers and figuring out the rules that make quantum mechanics work. And he was in a train, and by accident, his companion in the train was a German mathematician. The mathematician looked at what he was doing and said to Heisenberg, "Why are you doing matrix algebra?" And Heisenberg supposedly said, "What's a matrix?" And so he had just kind of invented this to make it work. So that's going to be our rule. And the really important thing is this bar, because the bar means take the adjoint of the operator on the left, then do the multiplication. Remember that our recipe for finding an observable quantity was to multiply the density operator times the operator for the quantity, and then take the trace. No adjoints. So you can get very confused because the two formulas look very similar. It just depends whether there's this vertical bar or not.
Seems to be true that he works on trains. And I remember that somebody else later told him that when he was calling, something like tableaus were actually matrices and were known. So the essence of the story is right, but it didn't happen all one day.
Okay. So on this side, how we got ahead ourselves. So here now, on this side, I can apply orthogonality. I'm going to say that this term is 0 unless j and k are the same. And that means on this side, the equation collapses to just the jth term. And then over here, this result depends on the result of the commutator. And I don't know how to work that out yet. But I'm going to say for the time being that because this is multiplied by an I, I'm expecting this to be a frequency. It's usually if I solve this first order differential equation, I'm going to end up forming the exponential of something. And the exponential of I times something times t is going to look like a frequency. So not knowing what this is in the brackets here, but thinking that it's going to look like a frequency, I've called that omega sub jk. And that's to mean everything in this bracket. Now, because I'm taking to eventually the product of some operators and then calculating the trace, the result is going to be a number. So this is omega jk here is some number that I'm going to think of as being some frequency. Now in writing here that this is either 1 or 0, I'm assuming that I normalize the operators to magnitude of 1. But if that wasn't the case, I just have to divide both sides by whatever that magnitude is. So I've shown that more generally here, where I might have to normalize by whatever the result of the trace of adjoint b sub j times b sub j, if that didn't happen to be 1. And this is why you might wonder, why do I divide by b sub j's magnitude? Why not b sub k's? But this is why whatever we normalize the operators to, the entire basis has to be normalized to the same thing. So that this doesn't matter whether I thought I should divide by the magnitude of b sub j or the magnitude of b sub k. As long as they're normed the same, I can do whatever I want. So that's why it's so important that we might imagine we've normed the unity, but frequently they're not, because if we norm some of these operators to unity, you get a bunch of square roots running around, like the square roots. So the middle would be true for arbitrary norming, and then what's written on the right would be true if we had normed to 1. The end result, and this is the important thing, is we've reduced an operator equation or a matrix differential equation, which makes you all nervous, to a simple algebraic equation. This is just a set of coupled first-order differential equations for numbers. And Mathematica will trivially solve this for you by setting up many ways of solving this. Formally, we would solve this then by just multiplying by dt and then integrating. We could do a Laplace transform, convert it to an algebraic equation, and then solve the algebraic equation and do an inverse Laplace transform. It can be solved numerically on a computer, just feeding the differential equation into Python, which knows how to do numerical solution for differential equation. So by doing this expansion in the basis operators, we then taken this rather unpleasant differential equation of matrices or operators and made them just to a plain old vanilla algebraic set of differential equations. If we have n basis operators, we're going to have n differential equations, and they're going for k, capital K basis operators. We're going to have capital K differential equations, and they're going to be coupled together because they're going to share frequencies and stuff. But it's just algebra at this point. This is really for kind of the future in that later on, when we come to relaxation theory, I'm going to invent more symbols. And here, the script L means take the commutator. So that's called the Liouvillean superoperator. Something will reemerge later. And its whole purpose is to make all of this look simpler by hiding the commutator, but we end up with the same result, where now these elements of the Liouvillean are what I call the frequencies. The end result is the same, but again, I put this here just to say you'll see this again. So here's what we end up with at the end of the day. We have the magnitudes of all these basis operators. I had called them little bj of t previously, but now I'll frequently use this symbol to mean the magnitude of the operator as a function of time. The literature, how people talk, is kind of loose. We talk about evolution of the operator, but the operator never changes. The basis operators never change. It's the coefficients that change. The language is a little loose. But these are the algebraic coefficients that previously were the b sub j's. And here are the frequencies. Here's the differential equation written out at a big matrix, which is how Python or some other program would solve. Any questions online? You might
No
notice,
question. No question for me.
okay? You might notice here, if we forget about relaxation for the time being, this final matrix equation is mathematically isomorphous to the block equations. It has frequencies that connect different terms. For the block equations, we just had the magnitude of the X magnetization, the Y magnetization, and the Z magnetization. Now we have any number of operators depending on what our basis operators look like. If we're just talking about one spin, we just have the three basis operators, say Ix, Iy, Iz, and then the identity, or I alpha, I beta, I plus, I minus. So depending how we write it, it's a 4x4 matrix or a 3x3 matrix. If we have two spins, we're going to have 16 basis operators that are going to be things like Ix and 2Ixsz, so on and so forth. So this is going to be, when we stack it up, potentially a vector of 16 coefficients corresponding to the 16 basis operators. And then the capital omegas are going to be a 16 by 16 matrix. But Python or Mathematical won't care. So we've turned everything back to look a little bit like the block equation, which is the real kind of fundamental property of thinking of this operator expansion. Before this was thought up, people wanted to try to figure out a new pulse sequence. They were looking at all these matrices and trying to figure out what was going on. So a pulse sequence that won't really come up in this class because it's really mostly used for small molecules, but maybe I'll put it on a problem set is called depth. It's similar to a net, or similar to a refocused net, and that you can take magnetization from protons to carbons, for example. But it's a very clever overlapping of spin echoes and J evolution periods and things like this. And the thought that people manage to figure this sequence out just looking at tables of matrices is sort of astonishing, but it's not hard to work out how it works with these operators instead. So it was I think, 1983, when simultaneously 3 groups invented this operator decomposition of the density operator. Kind of an example of things are in the air. And sometimes multiple groups are working on the same thing. In this case, 3 groups had the same idea come out the same year. So these couple of slides are critically important. So make sure you understand these couple of slides. And you'll get some practice on the problems. Okay, well, the question has come up, what is coherence? It's come up before. So coherence, one of these things in quantum mechanics that you may not understand, but you learn to use it in a sentence and use it to solve problems. There's the old joke of a student rushing up to Feynman and saying, Professor Feynman, what is the meaning of quantum mechanics? And Feynman says, shut up and calculate. So there's a little bit of that in NMR. We have a recipe for calculations that it works is enough at some level. But here, let's talk about how coherence a bit. So, for example, if we took I minus for 2 spins, then I have to remember what I mean by I minus is the direct product of I minus with E, the identity operator for the S spin, because I haven't written SZ or anything anymore. And when I do that calculation, here's the matrix that I get. And I think about what I mean by coherence then. And now I've written the 4 spin states in their order across this matrix. And remember I said that in my definition of the wave function, I order them where the rightmost index changes first. I start with alpha alpha, and I have alpha beta, and I have beta alpha, and finally beta beta going down the column. And then if I take the transpose to get the row, across the top I have alpha alpha, alpha beta beta, alpha beta beta. And when I look at my matrix there, I look and see where I have 1s. There's a 1 that says I link alpha alpha to beta alpha. And that's what I expect I minus to take the alpha state to the beta state. And I means acting on the first element in the wave function. And then I have another 1 there, and that links alpha beta to beta beta. And again, that's what I expect. I minus to take alpha to beta. So I think of then the matrix as representing a coherence linking those pairs of states. Now, again, let's go back to just the single spin. Ask what we mean here. The typography is bad, but for example, if I have a single spin, then in some density operator, if I expand the density operator in terms of I alpha and I beta, IZ, etc., then this is going to convert I alpha into some combination of alpha and beta, depending on the operator. And then when I multiply and integrate with the bra alpha, I'm going to pick out only the part that remained alpha by orthogonality. So here, I end up with some coefficient associated with the amount of alpha that I had. And this in general is going to have to be average over the ensemble. So the bar here is the average over the ensemble. Here, I mean, this, I have to space these out. This is now a separate calculation. Alpha acting on beta. And I'm going to now get back a different result. And now there's an explicit phase difference between the two. I've pulled out this is some complex number. So here, when I took the square, the phase parts went away because it was the same number. But here I have two different phases. So I've separated the magnitude of the two complex numbers and the two phases. Now, and similarly here, the beta beta, I just get some number, the phases cancel. Here, the beta alpha, I also get some phase difference. And the important thing then is if there's no coherence between the alpha level and the beta level, if I haven't introduced any phase coherence, then that difference in phases is going to be random from one set of molecules or set of spins to another in my sample. And when I average over all of the spins, those phases are going to go to zero because the exponential is just cosine of a phase plus I sine of a phase. And if I average over the cosine over all angles, I get zero. And if I average the sine over all angles, I get zero. So if I don't have any phase coherence, these terms are going to go to zero. And I'm left with only the diagonal term and the resulting density. So when I introduce phase coherence, again, by having the pulse applied to the equilibrium density operator, that's saying now that there's some phase relationship between the alpha wave function and the beta wave function that doesn't vanish when I average over the whole sample, and then I'm going to represent that as the I minus or I plus operator. And when you see a picture, it'll be a squiggly line connecting to the two levels. That's different from thinking about a transition. There's also transitions when you flip a spin from beta to alpha. And obviously that's happening when you do a pulse. But coherence is more specialized because if I flip the spins incoherently, then I'm going to end up again with magnetization spread out in the transverse plane, and the average will be zero. I didn't create any coherence. I don't have any transverse magnetization. So I'll generally draw transitions with straight lines connecting two levels. That doesn't imply that there's any phase coherence across the sample. Every little sub-ensemble in the sample could be doing its own random phase thing. But the squiggly lines imply that I imposed phase coherence across the sample. And my way of doing that is starting with Z magnetization and using a phase coherent RF pulse so that every part of the sample sees an X rotation. Okay? These are all kind of subtle differences, which is why eventually you forget, you don't understand what it means and you just use it. Yeah?
I'm still finding it difficult to understand what you mean by linking these two states in coherence.
It's a mixed state, okay, so normally we think about eigenstates as states that can live stably forever, they're the stable states of the system. If you have any state that's not an eigenstate, by definition, it may not be stable. Let's say this optical system or IR system, it may be so unstable that we don't care about it. It's just going to decay to the ground state. There's nothing you can do with it. There's nothing you can measure with it. It's just unstable. We have a funny situation that you can have an unstable state and it lives long enough to make measurements. And its observables are orthogonal, different, distinct from the observables of either eigen. So a mixed state has its own set of properties. And we use the word coherence for it for the reason that Art said, that if you do a single particle measurement, of course you will measure something. But we're not doing single particle measurements. And so there's a sense in which you have to do the same thing every time. Like you can't like make alpha plus beta over here and then alpha minus beta over here. You have to actually do the same thing every time or to every spin in order for it to add up to something. In other words, if a mixed state has new properties, there may be many mixed states with many different properties, and we're not interested in averaging over all that because it might average to zero most of the time. So you want to prepare the same mixed state every time. That's what we mean by coherence. It's a meaningless for a single particle experiment, but if you have the whole ensemble, it means essentially do the same thing, make the same mixed state.
So in a mixed state, we don't have these just eigenstate of.
Yes, and it cannot live forever. It's not the stable state of the system. It's not the top being up or down. The top is in the wrong place in a classical picture. It's going to evolve out of that. It can't stay there. So it's interesting, right? It's interesting. It has observables. They'll change over time. It won't live forever. That's coherence. Not stable. But many of them are so short-lived, they're not even interesting, but in NMR we'll get to play with them. We're lucky. Medium case, right? It lives even shorter amount of time.
And in part because they live a long time, it's easy to make a source of electromagnetic radiation that is spatially and temporally phase coherent. And that problem was solved by radar engineers in the Second World War. And unsurprisingly, NMR was invented after the Second World War. Spatially and phase coherent optical systems are much harder. As Ann said, the lifetimes of these states are much shorter, and it's much harder to build lasers, for phase coherent on these much faster time scales. So we're kind of lucky. So for two spins, we know we have 16 basis operators. The matrices are 4 by 4. They have 16 elements. So there must be 16 basis operators. And here's one way of writing them using the I alpha, I beta, I plus, S plus. And what's nice about these is they show kind of directly reference back to operators derived directly from the wave functions. So if you write a bra ket, that gives you a number. You're multiplying a row vector by a column vector, and that generates a number that's either 0 or 1 from the orthogonality of the wave function. Here I've reversed it. I have the ket bra. So now it's a column matrix multiplying a row matrix, and that gives you an n by n matrix. That gives you a new matrix, sometimes called the outer product. So if I write the ket bra, those are operators, and I can then show, for example, that the ket alpha alpha acting on the bra alpha alpha is what I mean by I alpha S alpha. if I take the I alpha matrix and do the direct product with S alpha, I get the same matrix. So those top four, I think of as the populations of the four eigenstates. My two spin system, I have alpha, 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 beta, beta, alpha, beta, beta. And those operators then return the population of each state. And then I have what we'll call single quantum coherences. These have either an 1 plus or 1 minus. And you can see they depend on which spin changes. So for example, the alpha alpha acting on the bra alpha beta, the S spin went from beta, started, everything works from backwards, right? From right to left, not left to right. So beta went to alpha, so that's an S plus, whereas the I spin stayed alpha, so that's I alpha. So I can look at these and write down what they mean. And if I want the matrix, then I then just have to take the column that corresponds to alpha alpha, which would be 1, 0, 0, 0. And then the row vector that's alpha beta would be 0, 1, 0, 0. And then just multiply them together. And that would be the matrix representation of I alpha S plus. But you can see I have all the combinations. And then there are so-called zero and double quantum coherences, in which the sum of the up and down is either 0 or 2 or -2. So for example, the alpha beta acting on the bra beta alpha, the I spin goes from beta to alpha, and the S spin goes from alpha to beta. All right, go from left to right, right to left. You're right. So that I recognize as I plus S minus, and that would be called a zero quantum coherence or a flip-flop coherence. One spin flip, the other one flop. And then there's the corresponding one, where the I spin is minus and the S spin is plus. And then there's a +2, where both spins go from beta to alpha. And there's a -2, where both spins go from alpha to beta.
One of them is flip-flop, the other one is flop-flip, or does that not work?
Usually people just say flip-flop for everything and then flip-flip for the ones that go together. Yeah.
You use Q here as the coherence order,
Yes,
and then when you look at coherence terms for pathways,
yes,
for
it's
experiment.
the same thing.
Yeah, but how do you tell difference between population and zero quantum coherence?
So for phase cycling, you can't. So when you talk about phase cycling, so this is an orthogonal basis set. The matrices are all orthogonal if I multiply them and take the trace. That was my. Later on, when we talk about phase cycling asks, how does an operator respond to a rotation around Z? And the zero quantum operators and the longitudinal operators all behave the same for a rotation around Z. The longitudinal ones don't know about rotations around Z, but these say this operator is going to rotate, say, clockwise, and this one is going to rotate counterclockwise with a net of 0. So you can't tell by phase cycling. You can't distinguish them. And that means just Z rotations don't define an orthogonal basis That's not enough to define the orthogonal basis set. But this will come up later. I kept promising to show what this looks like on the energy level diagram. So here I have my 4 states labeled with the operators that represent the population. And now here I have the squiggly lines to represent coherence. So this is the alpha alpha state. This is the alpha beta state. So this squiggly line represents I alpha S minus. The S spin went from alpha to beta, and the I spin stayed alpha. And here's going the other direction. I alpha S plus is phase coherence in the opposite side. So on and so forth. So now I've labeled all of the single quantum coherence lines, the squiggly lines. And now down here are the double quantum, the flip terms. Here we go from alpha alpha to beta beta, that's I minus S minus. Here we go the other direction. And here are the zero quantum terms, the flip flop terms. So in this basis of the pluses and minuses, the alphas and the betas, the operators have a direct link to the eigenstate, the picture I can write on the eigenstate. Of course, if I want to think about the Cartesian basis, I then have to take various linear combinations of these to get to the Cartesian basis. And in doing that, I know, for example, that IX is 1/2 of I plus I minus. IY is 1/2I plus minus I minus. So, and then I alpha plus I beta is identity, and 1/2 of I alpha minus I beta is what I call IZ. So I can transform from this set of operators, which is very convenient for thinking about how everything relates back to the energy level diagram, to Cartesian operators. Let me see. Somewhere table of all the Cartesian operators has disappeared. That's weird. I'll put a slide that shows a set of Cartesian operators, but they're IZSZ, 2IZSZ, IX, IY, SX, SY, SX, SZ, so on and so forth. Now, what's really phenomenal is the operators are coherence. These are the population. These coherences give rise to the frequencies in an NMR spectrum. So if I look, here, for a 2-spin system, I get a doublet centered at omega I split by the J coupling, and the doublet is omega S split by the J coupling. And then this line, which line is which depends on the sign of the J couplings and the gyromagnetic ratio. So which way is which is a little tricky. I'm going to pretend that I have positive gamma and positive J. Yeah. So that this line here represents coherence between the alpha alpha state and the beta alpha state. So that it represents I minus and S alpha. This then is I minus S beta. The other partner, this single quantum for the I spin, and the S spin has its same state. Similarly over here, this is the connection between alpha alpha and alpha beta. So the S spin has changed its state, and the I spin is in the alpha state. And here is beta alpha to beta beta. Oh, that's a typo. This should be I beta S minus. Here. Wow, that typo's been there for decades. So we have, and what's really remarkable about NMR is this very direct link between the peaks that you see every day in the NMR spectra and what seems like this rather abstract operator calculus that we worked out starting from the Schrodinger equation. In the end, it's really simple. All these symbols have direct meaning in the NMR spectrum. Are we doing? Oh, got some time. Here's just some examples of switching between the different basis sets. What does this operator need? Mapping, raising and lowering operators, etc. You can look at this just to get some practice with these manipulations. This picture just kind of formalizes the operator space for different transformation. So this says that if we have a trio of operators and they obey a commutator relationship shown there, that the commutator with A with B equals I times C, then we can draw this kind of picture in operator space that under a Hamiltonian proportional to C, A evolves into B and with these trigonometric relationships. So that's a general statement of the rules that we're about to derive and we have derived. I'm not going to prove that. So then we write down a bunch of rules. And the rest of analyzing NMR pulse sequence, say, is applying these rules over and over again. So chemical shift, we know that IX evolves towards IY, a right-handed rotation with my thumb along Z. So IX evolves IX cosine omega t plus IY sine omega t. IY rotates towards minus IX, so I get IY cosine minus IX sine, and IZ doesn't evolve into the chemical shift. And then I have some rules for scalar coupling. So here I have IX evolving. Here's the picture that I draw, and then there's the algebra. IX, the scalar coupling is proportional to 2IZ SV in the weak coupling limit. And then I have IX going towards 2IYSZ. So what does that mean in practice? In practice, IX is IX S alpha plus IX S beta my in-phase doublet. And then when they evolve towards plus or minus y. So I'll end up with something that's IYS alpha minus IYS beta. And then I alpha minus I beta S beta is proportional to SZ. So this just says the IYSZ says I've evolved to where my two doublet components are pointing in opposite directions in the transverse plane. And in our mathematics, we're forced to call that a Z operator. And we recognize that in the spectrum because now we have an antiphase sense. So here's IY, SZ isn't affected. Here's how the antiphase terms evolve back to in phase. If we have an antiphase term, eventually they'll come back to in phase. And here's 2IZSZ, it doesn't evolve under the Z rotation. So I can memorize the pictures, or I can memorize the equations. You'll notice that the pictures always have Z or Z, X, and Y. So it's still kind of a right-handed coordinate system. And then I can put two new Z operators on here and wherever I want. I can put it here or I can put it there depending on the evolution. So when I started doing NMR, I just had pictures like this taped up on the wall at my desk until eventually I memorized them. And then pulses. We know an X pulse does nothing to X magnetization. An X pulse takes Y, X should take Y to plus Z. And Z goes to minus Y with the next pulse and so on and so forth. So that's it. Those three figures are everything we need to know to work our way through a pulse sequence bit by bit. Most pulse sequences are a pulse, a delay, so another pulse, another delay. So we just do it bit by bit. Use these rules for the pulse, use the rules during a delay to evolve the chemical shift and scalar coupling, use the rules to apply the next pulse, and off we go. And then at some point, we need to detect. So here are things we already know. If we apply a Y pulse, we get X magnetization. I can write X magnetization in the raising and lowering part. What's nice about these raising and lowering operators is evolution is just a phase for those operators. So I plus requires a negative phase that depends on the frequencies. And I minus requires a positive phase, which depends on the frequencies. That's a little bit confusing, and to keep that in mind. The signs are crossed. Plus requires a negative phase, minus requires a positive phase. That's a little simpler than the evolution in Cartesian space, because then X turns to Y, Y turns to X, etc. So I've just written this all out. And so this is the result of evolution during an acquisition period after a pulse. And then my rule for detection was to multiply by the detection operator and take the trace. So I'm going to pretend my detector is tuned only to the I spin, so maybe S is nitrogen. So the detection operator is just I minus, and of course that's I minus S alpha plus S beta in reality. So I multiply. If I call the detection operator then F plus, I take my density operator that I just worked out, multiply it by F plus and take the trace. The trace isn't changed by a cyclic permutation. So it doesn't matter whether I did sigma F plus or F plus sigma. So here I wrote sigma F plus, but it wouldn't matter. And I just multiply everything out, remembering that my operator basis is orthogonal. So F plus will only pick out minus operators because of orthogonality. So here's what I end up with. And this is exactly what we expected. We expected to see an in-phase doublet. The two components have the same sign. They each have magnitude a half because the line is split in two into the doublet. One is shifted up in frequency by pi j, the other is shifted down in frequency by pi j. So the difference is 2 pi j in angular units or j in hertz, which is what you expect. But this is always going to be true. Every operator Ix at the start of acquisition is going to generate an in-phase doublet. So we actually don't have to do this calculation anymore. All we have to do is say, at the start of acquisition, I see I have an Ix operator that's going to generate an in-phase doublet, end of story. So actually, well, acquisition seems very important when you sit and look at the FID being acquired. From the computational standpoint, it's not very important because once we recognize the basis operators present at the start of acquisition, we already know the line shape. We don't have to actually calculate evolution. The only thing that would change is that if we decouple, we would collapse these two lines into the center because decoupling would remove the J's and we would just have a single line. What happens, is what we just said, we call that an in-phase doublet. Suppose that we have this operator. And again, at the start of acquisition, I do the same thing. I work out how the operator evolves during acquisition period T. I take the trace. And I find what I already assumed, that that's going to give the antiphase doublet. That operator represented two vectors pointing in opposite directions in the transverse plane, one associated with the S spins in the alpha state, the other one with S spins in the beta state. So when I acquire that signal, I get one doublet component up, the other doublet component down. So I don't have to do this calculation anymore. If I see at the start of acquisition, 2 pi xsz, I say that I'm going to get a antiphase doublet. One component up, one component down. If I happen to decouple, I'm going to get 0 because those two are going to be on top of each other. This requires that there is a J coupling, by the way. If there was no J coupling, then I'm going to continue just to have this operator, and that will give no signal at all. because it's going to be orthogonal to the detection operator. It has to evolve in order to become detectable. It can only evolve into something that's detectable if there's a J couple. So if we decouple and there's no J coupling, there's going to be no signal. Or if we created that operator in some way by some other J couplings, and now we have this term, and there isn't any J coupling between these two, then we're also not going to see any signal, because the J coupling has to evolve. So we'll always say, if we see this operator, this is going to be an antiphase doublet, but in the back of our mind, we have to remember if there's a J coupling. And by convention, we'll say, if we have an X operator, that can be phased to be absorptive. So here I would say I have absorptive line shapes and they're antiphase. The previous one, I would say I have absorptive line shapes and they're in phase. And then by convention, if I had IY, I say that's going to be dispersive. So if I have an IY operator, I'm going to get in phase doublet, but the line shape will be dispersive. And if I have two IY as Z, I'm going to get antiphase doublet, and the line shape will be dispersive. Of course, on the spectrometer, I might be able to rephase, but formally in the mathematics, because I might have in some experiment some terms that are in phase, that are absorbed, that are IXs, and some terms that are IYs, and I can't phase them both. Whatever phase I apply is going to be applied to both. So our convention will be an IY is dispersive, IX is absorptive. If I have an antiphase operator, that's an antiphase doublet. I have an in-phase operator, that's an in-phase doublet. If I have two, back here, this picture, if you go back and look at the picture that actually had energies on, you would find that the effect of the J coupling is either to move this level, and these down or up. Doesn't matter. This level either moves down or up, and this level moves by the same amount due to the J coupling. So the energy difference for the two quantum levels is unaffected by the J coupling. And that means if we have an operator like I plus S plus, it can never evolve into something we can detect. It can never become IX or ISX or I minus. It's stuck there. So anything with, and the same thing is true for the zero quantum. They move in the same direction. These moved up, these moved down, vice versa. So the zero quantum terms are also independent of the J coupling. So if we have something like I plus S minus, it's never going to be detectable. And that means that any operator with two Cartesian X or Y terms can't be detectable because they're always combinations of the pluses and minuses. So if we have two IXSY, doesn't matter how big the J coupling is, that's never going to evolve into something we can detect because it's insensitive to the J coupling. Only terms with a single transverse operator are detectable. And then we parse out, are there in-phase couplings, antiphase couplings, etc., and is the line absorptive or dispersive? So this is a great simplification. We don't have to do any calculations as to what's going on during acquisition. We know by inspection what's going to happen during acquisition. This slide is probably of conceptual interest to me, but not to you. Here, because the trace is cyclic, I can move an operator around. So go back to here. I have the density operator was exponential with the Hamiltonian, Ix exponential, and then F plus. And I can move this to the other side if I want, because the trace is unaffected by a cyclic permutation. So I can then make this look like the Hamiltonian is operating on the detection operator in the backward sense, leaving the density operator alone. And that's worked out here to show that you get the same answer. And this is really just to emphasize that this is the operator at the start of acquisition. And this is just to emphasize that all that's important to us is, does the density operator at the start of acquisition contain some I minus SF? If it does, we're going to get this signal. And if it doesn't, we're going to get nothing. And same thing over here. So that's a mathematical way of telling you what I already said. We don't have to do the calculation during acquisition. We have to identify at the start of acquisition, does our density operator have components that match what we're able to detect? And our convention, it could have been chosen differently. The convention in NMR, we have to put the signal together to do a complex Fourier transform. And the convention is to put the signals together in such a way that our signal looks like it's proportional to I minus. So Ix minus Iiy. That's why this I minus is here. We could have chosen the other way. It doesn't matter. We had to make one choice. If you're measuring the X signal and the Y signal, and you want to combine them to be a complex number, you could have added plus Iiy or minus. Somebody decided long ago to have it be I minus, and that's just the way it is. It's a little convenient because remember, I minus develops a phase. It's a positive phase shift. So maybe that's nicer that your detected signal ends up having positive phase. Well, plus and minus. But that's the convention. So that's the cyclic property of the trace is useful sometimes when you're doing calculations. And one of the problems in problem step 2 makes use of that just to drive point home. Of course, if we have 3 spins, things get more complicated because now we have many more energy levels to work on, and now we have more scalar couplings, and puts in important to remember that each scalar coupling is either generating an in-phase doublet or an antiphase doublet. Now, if the first coupling generated an in-phase doublet, and the second coupling is antiphase, then you're going to have 4 lines, and each of the original lines is going to be split into an antiphase doublet. So you're going to have 2 positive doublet components and 2 negative doublet components. The easy way to keep track of this when you're trying to figure it out is start with whatever the biggest coupling is and work your way from the big couplings to the small couplings, because that way lines don't cross each other and it's less confusing if the lines aren't crossing each other. Maybe there's an example here. There's certainly an example for you to work on. Notes. Here, of course, if I have 3 spins. What I mean by IX is IX times the identity operator for each of the other 2 spins. I call the spins here I, R, and S. So IX means IX times the identity operator for the I spin, the identity operator for the S spin. When I multiply these all out together, I expect to get then 4 components in the multiplet, 4 different signals. And this one is going, assuming the couplings are all positive, this one is going to be at the sum of the 2, J coupling. So that's shown here. And then this one is positive, negative. So here I have the difference of the 2 J couplings. Here's the other way, and here's the other way. I have 4 lines, they're equal intensity. And I can assign to each line a frequency and what operator represents. What would be different, suppose that I had IX, 2IX, SZ. This would still be the identity. I would have the 2, SZ is a half, S alpha minus S beta. The 2 and the half cancel. So whenever I had S beta, I would have a minus sign. So now I would have 2 lines that were positive and 2 lines that were negative. And these would be I could figure out the frequencies. So just to give essentially here. So here's the example of 2IX plus Z, where I pick up the minus signs to repeat. And we would say, looking at the operator, looking at this operator, we would say that this IX operator is in phase with respect to the R coupling and antiphase with respect to the S coupling, and so on and so forth. This operator is in phase with respect to both the R coupling and the S coupling. And here is what I meant by starting with the large coupling. So the IR coupling is bigger than the IS coupling. First, I would say for this operator, I have an in-phase doublet for the JIR coupling. And then I have an in-phase operator for the JIS coupling. So each of these lines gets split into a multiplet split by JIS, and I have 4 lines. And if I had the other operator, I would say the operator is in phase with respect to JIR. So I split into an in-phase doublet, an antiphase with respect to JIS. So each of these becomes an antiphase doublet. And then I see my four lines again with the lines up and down, so on and so forth. And you can probably see that it's possible for certain combinations to get cancellation between positive and negative, which can be confusing sometimes in spin systems. Okay, that's enough for today. We covered a lot of ground. Review the notes and come back tomorrow with questions, because as far as analyzing pulse sequences in the absence of relaxation, we now have the tools, pretty much all the tools we need. We know how to propagate forward from equilibrium density operator, first pulse, first delay, and then at the end, right before acquisition, look at the operator terms to figure out what the line shapes are. So a lot of it is practice, practice, practice now. And at least for the solution part, the first new thing will come in the form of relaxation. Before that, Anne will introduce tensors. For the next couple of lectures, we'll be practicing. Okay, so we're going to have a problem set while we swap computers. Everybody can stretch. You have to log into this Zoom.
Oh, that's right.
I will stop sharing.
That's a first.
Yeah. Okay.
I guess I can be heard online. There are too many people. Couple people. Hello? Okay, so I wanted to continue this where we stopped last session, which was the last problem in problem set 1, where we were looking at off resonance effects of 90-degree and 180-degree pulses generally last class, and we were looking at this problem where you had an offset of 10 kilohertz and B1 field also of 10 kilohertz, which gave you this sort of situation where capital omega omega 1 are kind of like that. So the effective field is an offset is at an angle of 45 degrees. And we calculated the magnetization at the end of that pulse. This is the expression that we got. This is this vector in 3D space that gives you the amplitudes or coefficients for the 3 components, the magnetization along x, y, and z. And we said that the amplitude of the signal will equal the signal that is when you turn on the receiver. So we checked with the square of the sum of the squares of all the 3 coefficients equals 1. That's consistency to make sure we haven't made an error in the calculation. The question is asking what is the amplitude of the signal at the end of that pulse relative to an ideal on resonance pulse. So an ideal on resonance pulse gives you unity in signal amplitude. Relative to that, you get this quantity. It's the square root of the coefficients for x and the coefficient for y. Is the amplitude of the signal when you turn on the receiver, because that's transverse coherence, which will give you a trace with the detection operator. And this is the way by which you calculate the phase. Just for completeness, we will then move on to another problem from the same problem set where we discuss much the same thing. But what I've drawn here on the left is the projection of that magnetization vector in the xy plane. So the amplitude of this vector is what gave you signal in the FID. You wanted to calculate the phase with respect to minus y, and I'm doing minus y because if you think of an ideal 90-degree pulse that is phased along x, so an ideal 90-degree x pulse will give you minus y magnetization. So ID on resonance is minus y. Relative to minus y, I can define a phase angle phi, and that phi will then have a tan which is given by this x component. That x component comes out of this matrix multiplication here, and a y component divided by the absolute value of the y component, which is something like that. That's how you would calculate the phase angle, or the phase, generally speaking. Phi is tan inverse of this. That will give you the phase of the magnetization at the end of this off resonance pulse. Now, the next question that I want to briefly go over before we move on to the second problem set is an interesting one. It's also about off resonance effect.
Can I say something about
Yes.
that solution, which I haven't noticed before? Of course, a 90-degree pulse, alpha, maybe I'm wrong. Alpha turns out to be √2 greater than the 90-degree. I think in this case, alpha was √2 times I/2. In the beginning, when we calculated what alpha was, it would be
Yeah, because you have the 90-degree pulse length and the effective field is √2 times omega 1. So yes.
So we have the tangent. I'm just wondering if we could reduce that tangent to something we recognize.
I see. So did I make a mistake here?
No?
Sorry?
Your excellent plan.
Well, this The first term is my X component. Tan phi is perpendicular over this.
If you do 90-degree like substitution, you have
Well, Z is going into the board. That's how you.
You have Z going into the board here?
Yeah,
Ah, okay,
Z going into
then
the
it's
board.
okay. But we're not measuring the phase here relative to the x-axis.
Yeah,
We want the phase relative to the minus y-axis, because that's where the magnetization would have ended up with an ideal pulse.
I have a feeling that this is actually supposed to be cotangent and not tangent. Maybe I'm doing this. If you 1 minus cos alpha is 2 cos squared alpha over 2. Sin alpha is
1 minus cosine alpha is 2 sine squared alpha over 2.
oh that's
cos alpha is 2 cos square alpha.
yeah. So it was I think you would have plus there. Then that is 2 sin alpha over 2 cos alpha over 2. Use those two, then you do get the tangent of alpha over 2. And alpha is square root of 2 pi, so you get like pi over 2 root 2. Tangent of that gives you. That's that number. I don't think it is simplifiable anymore because you get irrational inside the angle.
One thing you learn doing NMR is what your trig identity are.
Yes.
Make your high school trig teacher very happy.
The next problem is much the same, except that it makes you work through 3 by 3 matrix multiplication that we did last time for a general flippant alpha. So here you're looking at of resonance effects of a 90-degree pulse length of P, and you're saying that you are not far off resonance, you are still close to the resonance range. So you need to show that the off resonance effect can be approximated as a 90-degree pulse that is ideal, followed by a free precession period which is given by 2 tau p over pi. So something like this. At the end of this pulse followed by a delay, magnetization would be in a similar situation as to what it would be after just the off resonance pulse, where the off resonance effect is limited or it is small. The way that I like to do this problem is to just take this result, which is the full on off resonance rotation matrix, and then apply it to 001, 001 being the magnetization at the start of the experiment. And this is what you get. If you just applied theta equals 45 degrees, theta here is the angle that the effective field makes relative to Z. If you just put in 45 degrees, then you would get the result that you saw here in this calculation. If we just put in it as 45 degrees, you would get this result.
What is theta for on resonance?
Theta for
If we were on resonance, what would theta be? Pardon? 90 degrees. So if we're a little off resonance, theta is just a little smaller than 90 degrees. When the problem says we want to look at off resonance, the close to resonance, we need theta is a little smaller than 90. And alpha, right? On resonance, if we have a pi over 2 pulse, off resonance, alpha would be greater than pi over 2. But we're saying it's not very much greater. We're going to be close to resonance.
So we calculate the phase of that this pulse in much the same way. Using mx. Again, I have a z going into the board in this diagram. And again, I'm going to assume that phi is the phase relative to the minus y axis. And then I calculate the phase using the same result. One useful approximation that we can make here is to assume the flip angle is roughly 90. We come up as we simplify this. This should give us again related to what we saw here. We got an alpha over 2 on 1 over the square root of 2, and here again we get cos theta.
You lost your absolute value sign.
So assume alpha is approximately 90 degrees. The tangent of something that is, in other words, I'm saying epsilon is the angle that Art was describing, that is the extra between flip angle 90 degrees. The approximate that is 1, roughly 1. Then we get that the phase and for small phase errors, and I'm not sure how familiar people are with Taylor expansions of trigonometric functions. And one of the things that you could do is for small angles, a number of trigonometric identities operate. So sine phi and tan phi for small angles can be approximated as just the angle itself. You want to say something?
No?
This is just interested in if the students have made an attempt at this and what the differences or questions or compared to what Anisha said so far, what you have, or where did you get stuck?
Yeah.
I know some of you actually tried these.
Yeah, I think the question itself said it had a hint about doing it to first order in the ratio. So I just defined that and then used that approximation and got similar estimates. Yeah, so it ended up being the same.
Right. Well, what do we think about theta when we have near on the resonance pulse? Right, it just means that the offset is quite small. So if you think about our effective field again, kind of like that. The capital omega is much smaller than omega 1. In this case, the hypotenuse of the triangle can be approximated as small omega 1. Right? Because technically I have square root of omega, square root of capital omega square plus omega 1 square. But in the event that capital omega is much smaller than small omega 1 square, I can approximate that as just the RF omega 1. So that leads me to this approximation where the phase that is acquired by the magnetization is roughly capital omega over small omega 1. Now, if I want to go back to this experiment where I have a 90-degree ideal pulse with a delay tau p, how do I calculate the phase of the magnetization at the end of this delay? Absent any scalar coupling.
You want the phase of the rotation.
Well, it will rotate through an angle that will become the phase, right? So, what art is saying is, the question is saying you apply a 90-degree pulse that is ideal, theoretically ideal, and then you have a delay that is tau p, which is the length of that pulse. And so you will rotate the magnetization through an angle. What will that angle do? Have chemical shift evolution during that delay.
Tau p times the resonance.
Yeah, so I'll get this. Right, so I have chemical shift evolution for a delay tau p, so then you gain this phase, which is given by capital omega times tau p. So from that I get this. Now the question is this a reasonable approximation? Comparison.
What do you do?
Question was probability of resonance effect of a pulse of a 90-degree pulse when tau p can be treated to first order as an on-resonance rotation followed by a free precession period of 2 tau p over pi. That's one. Then this becomes that, right? Now is this the same as this? The relation between omega 1 and tau p.
Pi over 2. Interesting.
I said 80 degrees.
I'm not sure I heard you right. I thought I was hearing 180 for this. And so tau p is, in other words, yeah, pi over 2 omega 1. If you substitute that in, you get the same result. Make sense? Okay, you can now move on to.
So what this means, when you start to apply the pulse, the magnetization is already starting to precess while it's coming down towards the XY plane. So you get some partial phase advance during the 90-degree pulse. But fortunately, this says, well, if we happen to have a delay after the 90-degree pulse, and we think that delay should be 1 over 2j, for example, if we shorten that delay by 2 tau p over pi, that'll account for the phase error that we would normally have. So many times in pulse sequences, 90-degree pulses are followed by delays. So it's convenient to get rid of this effect by shortening the delay by that amount. If you look inside modern pulse sequences, this little calculation, 2 tau p over pi, is everywhere to correct for these little phase errors that otherwise would accumulate. Now, if you do it the other way, if you start, say, with IY magnetization and apply a 90-degree X pulse, which you can do at home, now that you've seen how it's done, you'll discover the same thing works. And now it looks like there's an extra 2 tau p over pi first, and then the pulse. So when you start on Z, it's pulse then delay. If you start on X, on Y, it's delay then pulse, but it's symmetric. So the 90-degree pulse looks like 2 delays with a perfect pulse in the middle. And each delay is 2 tau p over pi. So that means later on in the pulse sequence, the first pulse is applied to Z. The initial delay doesn't matter, but later on, when you have transverse magnetization, Z mag, these little delays are subtracted off whenever we can in order to account for this effect. So it's so important. I think actually, when this was first realized, I think people wrote an entire paper just about this. It makes a big difference. So when you start to have many 90-degree pulses, these phase errors would accumulate quite drastically. And while here we said near resonance, we don't know how near you have to be. But it turns out, by numerical calculation, to work quite well for an offset equal to the omega-1 field. So actually, you can get pretty far from resonance and it's still pretty good. So on a practical level, it's really important.
Even though the trigonometry would not work at all. When
Yes.
B1 is equal to omega. The offset in the RF are equal, you absolutely cannot approximate this as just small omega-1. Okay, so that was about problem set 1. We move on to problem set 2 and start talking about coupled systems and spectra of coupled systems. The first 2 questions that we're going to discuss are like largely related or derivative of what we just discussed in class. And I picked out problem number 5 from the problem set, which is for a 3-spin system, which is I, S, and R, with this ordering of J couplings. Positive J coupling for both. And the IS coupling is bigger than the IR coupling. The appearance of the 3 spectra with the density operator at the beginning of the acquisition period is given by IX, IXSZ, and IXSZ I'm not sure if I'm missing a factor somewhere. I don't think I am. Anyway, we'll start with the first one. What would you see for IX?
There is like 2 and 4 in front, 2 in front of ISS.
Yeah. On the top. Thing happens when I transfer the problem to this. Oh, no. It's 2 IXSC and 4 IXSC RT. Okay, so what do you expect to see for IX?
IX in phase magnetization, right? IX in the presence of J coupling, right? In phase doublet and
One doublet?
in phase,
One doublet in phase.
not one. I don't know how many.
Just 2 doublets.
2 doublets.
A larger coupling
Okay.
separated by IS, and then you get the doublet of doublets smaller than the system.
This becomes the IS coupling. Becomes the IR coupling. For both couplings you have in phase. Okay, because you just have IX. The way that, of course, are elucidated how you think about that is IX is in fact IX times you using E for identity.
Mhm.
Yeah. E in the S basis and then E in the R basis. And then E is S alpha plus S beta. E is again R alpha, R beta. So you get pluses all throughout. When you open brackets, you get S alpha, R alpha, S alpha, R beta, S beta, R beta, S beta, R alpha. You get pluses all throughout. So all of them have the same sign. So you get in phase for all for everything. Okay, what happens for 2IXSZ?
One of the doublets is negative or antiphase.
Which,
Well,
all right, let's make
is
this.
it better?
Uh, only one doublet?
What do you expect for the IS coupling?
The antiphase.
Thanks.
So the big coupling is antiphase.
The IR coupling is in phase.
Does it matter which is positive and negative?
Yes, it does matter.
Okay.
Crucially, it does matter.
Okay.
Because one of these two doublets is S alpha, the other one is S beta. Then, given the sign of the J coupling, you can determine. Here, the sign of the J coupling is given as positive. So, if I remember correctly, this is the alpha doublet, the left one, the S alpha doublet, and this should be the S beta doublet.
We hope.
Yeah, we hope. Assuming that this is the chemical shift axis for I. Yes.
This is a duplicate.
This is the actual NMR spectrum.
Duplicate.
Yeah. Typically, we, at least for heteronuclei, I guess maybe it's not familiar as much because we just do heteronuclear decoupling all the time. But you have to switch off heteronuclear decoupling. Use a pulse sequence that produces an antiphase coherence at the start of that position there. You will observe this. What happens to the last two?
This is how the closing.
Yes, so if you look at it, a homonuclear cozy spectrum, you
Yeah.
see these kind of patterns of alternated positive and negative peaks in the cozy from this effect, depending on how the couplings have evolved.
Some will be absorptive and some will be dispersive, and you can never get them all unless you do double quantum fission.
And even if you do fix the phase errors by doing double quantum filter cozy, you still see these patterns of the
Right.
J couplings, and people used to, like Walter Chazen has papers, Buttrick has papers working out. Well, for every amino acid, what's the pattern of positive and negative lows that you see? Because people used to have to spend a lot of time looking at the fine structure of the crossbeats in cozy spectra to try to figure out which amino acid they were looking at.
Yeah.
With heteronuclear experiments, you don't have to worry about that so much. You get that from
Either T.
E13. But you just had proton spectra, knowing what this fine structure was, depending on the branching of the side chain and everything else, was very important.
Okay, the last one. 4 IX SZ RZ.
Before we go on to that one, what would this look like if the two couplings were identical?
Yeah, you just get that. Or like the cube is upside down. You just have one.
Yeah, the two in the middle are gonna cancel. And it's gonna look like just an antiphase doublet with the wrong coupling constants. So sometimes you get confused, but you go back to the first one. Then if the coupling constants are equal, then you see a 1-2-1 triplet. And then you see all the time in organic chemistry, it's kind of bad. When you generate these other operators, and if the couplings are degenerate, then you can get cancellation effects that make interpreting the spectra more complicated.
Yep.
A question?
Period counts.
Right.
Can't hear you.
I know. I forgot my painkiller with me. Yeah, you said I need to switch level. Why?
Oh, okay.
I don't want to get pregnant, but oh my god. It's so I hate this.
Maybe like,
Last letter.
can you mute her? Or only,
I'm trying to do that.
I think she muted.
Suresh can do that.
She mute.
I don't think so. I don't, yeah, I'm not host, so I don't think I can.
I'll tell him that
Somebody needs to mute themselves for hearing your background conversation.
Okay, good. Message received.
Thank you. All right, let's be, so the next one, is that an RX or an RZ?
There again with my typos. RZ.
Okay,
IXSZ RZ.
so again, if we start with the big coupling, what do you expect?
In phase or antiphase? Antiphase. IXSZ, SZ, remember, is
Oh, sorry. Oh my
alpha
god.
minus S
Yeah.
beta. So in this way, if you see SZ, it's S alpha minus S beta, that's antiphase. You don't see S anything, it's identity, it's S alpha plus S beta. In phase. And what do you do for IR coupling? Antiphase. So what does that look like? At least here I know I have this. Then what here?
Down up.
That. Right? This is what I get for that term. 4 IX is 3 times C. Again, I am hoping that the more downfield is beta, and the upfield is beta.
And again, now if the couplings were equal, you would have a 1 minus 2, 1 triplet. You get very complicated patterns.
But does that have, I mean, CH2 group has like identical J couplings, but those are also, other than that, like, which is technically a triplet in the, is that the only situation where you can generate that effect? Other than methylene?
I refer you to Walter's paper in JMB about 1988 or so.
Okay, problem number 8. This one is very similar to what we also discussed in the lectures today. What NMR spectra are observed if the following operators evolved during the acquisition period? Two spin scalars coupled IS spin system. First is IX. So after problem number 5, this is trivial. Right, and in phase absorptive. What do you get for 2 IYSZ? up, one down because antiphase, is that it? So do I just have this? Are we all in agreement that this is what I get? No contradiction from anybody?
So where do you apply the pulse?
The same place I apply
Along X or?
the pulse is inconsequential. I just have this operator at the start of acquisition. I arrived at it through some set of process.
It should be dispersive, is that what you're saying? Because it's IY.
Yeah. So this would be what you would get if you had IXSZ. You have IYSZ. And assuming that receiver phase is uniform in this experiment, I'm not changing receiver phase. You should get a dispersive term there. Dispersive antiphase.
And again, it'll turn out, for example, in the cozy experiment, the diagonal peaks are IX and the cross peaks are IY. So you can decide whether you want the diagonal peaks to be phased to be absorptive, in which case the cross peaks are dispersive, or you can decide you want to phase the cross peaks to absorptive, in which case the diagonal is dispersive. But because the same phase is applied to everything, you can't make them both absorptive in the cozy. The generations of my friends as postdocs have tried to fix that problem, but it can't be fixed.
So you just do N50. Okay, the last one, 2IXSY.
Double quantum, right?
Is it only double quantum?
No, it's a mixture, right?
Of
Double and zero quantum.
yes. So what will happen if you turn on the receiver?
It's not observable. It's not observable.
So no signal.
So if I turn on the receiver and there's no signal, how do I know that term exists? Maybe I was lying to.
Can you give a about how you can evolve into something that is observable?
Well, how would I make it evolve into something? So of course, one thing I could do to prove it's there is right before acquisition, maybe I do a 90-degree X pulse on the S spin, in which case I turn that back into antiphase. And then I would predict that I'm now going to see an antiphase doublet. Or once we talk about 2D experiment, I could do the two-dimensional experiment in which this term evolves in the indirect dimension, in which case I expect to see evolution at 0 and double quantum frequencies, and then use some other pulses to convert back to something I actually can observe. So we know all of these terms that aren't observable exist because we can run, say, multiple quantum spectra, convert them back to observable signals, and see that the peaks are at the 0 quantum frequency or the double quantum. Our theory said they exist, but the spectrometer confirms it. There's also a fantastic thing about NMR, is we can go to the spectrometer and run a spectrum and convince ourselves that this theory was right.
this is a problem that Art has requested that we do in class. So we will do it. And I'm not sure we'll be able to do all of it today. Some of it is definitely highly non-trivial.
So this problem, when you get done with this problem, you know everything there is about pulses. So what I would suggest, I'll send an announcement out that we'll work on some of these in class because we get kicked out right at 3:30 today of this room. But I would suggest that you continue to try to finish these problems and then next week turn them in and so that we can give you feedback. Most of the problems, you're not going to get feedback for us, but we'll pick a few that are important enough that you'll turn in. You won't be graded, but we'll give you feedback on how you're doing because I'm afraid I know Anish can do them, and I'm afraid you might look at the answer keys eventually and say, "Oh yes, I understand this," without actually understanding. So I'll send an announcement, and then next week you turn them in, and then we'll get maybe some feedback on how you're doing. This is a pretty important problem.
I don't think I can do two of them. But we'll talk about that later.
Well, if you leave 5 minutes at the end, I'll talk about them, whatever it is, problem 8 or 9, or I'll give them some hints.
Okay.
The 8th or 9th one of these.
Okay, but the others we can start working right now in class. So the first one is, so the rules of the game, hard pulses for a given nucleus I and or S, but selective with regard to I and S. So you apply a pulse on I, you excite I1, I2, I3, all those excite up. You land a pulse on S, you excite all S spins. You have selectivity between I and S. With that said, how would you go from I1X to minus I1X? (180 on Y, right? Does it matter if it's Y or minus Y? Okay. The next one, 2I1Y, I2Z minus 2I1Z, I2Y.
(90° on X).
We are in agreement?
It's Y to Z and Z to minus Y. I guess minus X will work as well. Or no? It would be the same thing.
What I'm thinking. Will minus X work?
Either one should work.
Yeah. Accumulate a minus sign either way. X or X bar. Okay. 2y1x I2y minus 2y1x I2y.
Anybody online want to offer an answer?
Apparently no.
What was the suggestion?
180 on X or 180 on Y or just a 180 with any
Doesn't matter, the phase doesn't matter.
X, Y, X, Y, Y, but all of those will give you that. Or I1X, I2X, I3Z, to I1Z, I2Z, I3X. With one pulse.
I see on Y is that you're sending X to minus Z for the first distance and the negative cancels out. And then you send the third spin to positive X.
Y, or what about minus Y in this case?
This is what I'm trying to decide with that.
Pardon?
Minus.
Very easy. 3x times y.
Y takes you from Z to X, and then from X to minus Z, then you get two minuses. So pi by 2 Y pulse.
Whereas the minus Y is going to introduce a minus sign you don't want.
Yeah,
Mhm.
specifically, yeah,
Only one phase works.
because of this being a 3-spin operator, a 2-spin operator. Okay, now we get into what did you say? Shift operators. I was introduced to these ladder operators.
Both of them.
Yeah,
Lots of words for the same thing.
I1 plus I2Z to I1 minus I2Z. Because we always operate with phases in Cartesian space. Good to have in mind the conversion from shift basis, ladder basis to Cartesian. I1 plus in terms of Cartesian is given as
IX plus IY.
Ix plus
Is it not IX plus IY? Or
I
I
times
times IY?
square root minus 1 times y. And therefore this is given like that. This information what do you do? You can do it.
I think that also changed the Z.
Yeah.
It's clearly a 180, and now the question is which phase?
Yeah. It's not the obvious phase. Perhaps a clue. approach just at 180Y, which would do what you need to do to spin 1. Spin 2, it will also flip. See? Yes.
You just extract that many. So you get like negative pi. Then you take
I don't think. What's the pulse you're saying?
the 181.
180Y.
Yeah.
Ah. Oh, that's right. I guess I gave away the answer.
So 180Y inverts IX and IZ, and then you pull a minus sign out from the IX to cancel the minus IZ, and that gives you a minus IIY. And again, probably minus Y works too.
Yeah, as with all, most of these Y pulses for 2-spin systems or 2-spin operators, the
So the
Freudian Y bar.
thing is now, when you have, the first time you see the alpha, I beta, or I plus, I minus, the way to do it, as shown here, is convert back to the Cartesian basis, work out what happens in the Cartesian basis, and then switch back to the other basis if you need to. So since we're going to get kicked out in just a minute, so here as well, I alpha and I beta you want to express in terms of IZ and the identity operator. And then you can figure out what pulse you need. Let's do, you'll have to write that. One,
This one, these two.
yes, so this one. Here, when you have I1 minus I2 minus going to I1 minus I2Z, in this case, there's no single pulse that can transfer all the coherence from one to the other. And so what you're looking for is a pulse with a rotation angle beta and a phase phi. And you're going to try to work those out so that you get the most signal. You won't get one, you'll get some fractional amount that can be transferred. Back when I was a postdoc, people spent a lot of time figuring these things out as a way of optimizing sensitivity, in some complicated sequence, and there were theorems about it. And there's many ways to do this. But again, you can think about the fact, remember, a pulse of rotation angle phi, you can imagine that first you do the Z rotation to make it into an X pulse, and then do the X pulse and then undo the Z rotation. Well, that's one way of decomposing the problem. And in this case, that's useful because an I minus for a Z rotation just gets a phase e to the I plus phi. If you have some rotation by phi, it's just going to get that phase. And I plus is going to get e to the minus I phi. So it's convenient in this kind of case to separate these rotations into the phase rotation and then a rotation around the x-axis. So that hopefully then you can figure out the phase, then you figure out what the rotation by beta does, and then you find beta by calculus, by maximizing whatever function you have. You're trying to break it into pieces. So it's a tricky problem. And since we have to leave in 1 minute, we will, when you get to that one, if you need hints, email one of us. We can give you some hints. If there's one other like that, then the next one is also in that regard. And you can just see, this the pulse of arbitrary flip angle is going to generate many terms. But you only care about one term, the destination term. You're going to throw the other ones away and just ask, how do I maximize the one I'm interested in? In practice, sometimes you might not be interested in maximizing some term, but minimizing some other term. So the problem could be, it may be that there's some term that we can't get rid of by phase cycling, but we might hope we can adjust the phase somehow to minimize it. So, good. Have fun with these problems.
I think that was this. Right?
These are all recorded.
Oh yeah.
Yeah.
But you want to see the PDF of this session? Yeah, I can put it on Coursera. Hi everyone.
We're done. See everyone tomorrow.
Yes.